Hey everyone, a very happy Tuesday and welcome to our ARM Tech Talk series. It's another Tech Talk Tuesday and I'm super excited you could join us wherever it is you're joining us from. If it's your morning, your afternoon, your evening, it's great you could join us. This is the place for the latest and greatest trends, technologies, and best practices from ARM and our ecosystem partners. And I'm thrilled today that we're joined by Kernkonzept. This is actually the first Tech Talk we've done that has a real pure focus on an automotive theme. So if you've not heard about our Tech Talks before, really great to have you. We've got an hour-long session ahead, about 30, 40-minute presentation, 20 minutes of Q&A with a great demo today. And as I say, this is the latest place for the latest, greatest trends, technologies, and best practices from ARM and our ecosystem partners. So great you could join us. If you're brand new to this series, a particular welcome. I'm going to go through a few housekeeping items first. If you've been to one of these before and you're a series regular, you know the drill with these, but would love to just walk you through how you can get involved in today's conversation, what's coming up, and then hand over to Adam and Jan from Kernkonzept, who are going to talk us through today's presentation and demo. So Adam, if we can go to the next slide, please, that would be great. How you can get involved in the conversation? Well, you can tweet us using the hashtag ArmTechTalks, or indeed use that same hashtag for LinkedIn. We've done 65, I think now, or over 65 ARM Tech Talks, historically very focused on AI and the IoT space, and now we're in automotive, which is awesome. I'm super excited about this, and we've got quite a few coming up as well. So if you like what you see today, do sign up for your upcoming talks at arm.com/techtalks. All of those will be posted, if they're not live already, very soon. If you want a sneak peek of what's coming up, that's on the next slide on our table. So we have a talk today from Kernkonzept, next week Sonatus, and then the week after from NXP. All of these, as I say, are talking about the latest and greatest from ARM and our partners. So if you like this kind of content, make sure you're joining us on these webinars. Spaces are limited, so you can get an opportunity to ask questions to our panelists. If you want to do that, then spaces are limited. So make sure you register early is all I'd say. Just make sure you sign up as soon as you can. So today's talk, I'm really excited to have Adam and Jan joining us from Kernkonzept. They're going to talking about their L4Re Hypervisor and how they work together with ARM. Before I hand over to Adam, and he quickly introduces himself and Jan, they're in the same office, which is awesome, in the same place. If you've got any questions at any time during today's presentation, please just use the Zoom Q&A box, which is in the menu bar at the bottom, to ask any and all questions to our panelists, and I'll get to those at the end and be sure to ask the team at Kernkonzept. So Adam, let's get that camera on, and I'd love for you to introduce yourself and for Jan to introduce himself as well. There you are. And I'm now going to shut up. I'm now going to hand over to you guys. You guys are driving today's presentation. I'm super excited that you're talking about the automotive space and what it is you're doing here. We're thrilled you could join us. So Adam, Jan, it's great you could join us from Kernkonzept. Take it away with today's ARM Tech Talk, please.
Yeah, very much. Thank you, Tobias, for the introduction and giving us a chance to present here at an ARM Tech Talk. I'm here together with Jan, who will do the second part of the presentation. I'm myself. I'm Adam. I'm one of the founders of Kernkonzept. Have a very long, over 20 years of experience and history in the topics we're talking about, covering operating systems, virtualization, security around that, real time, and so on. You will get to know this today. And Jan, a few words about you.
Yeah, I'm Jan. I'm almost 20 years now in the industry. I've started in semiconductors, telecommunication, and so on. Worked a lot in system development and designing and architecturing big systems and diverse systems. And yeah, have a big knowledge in Linux and various operating systems. And yeah, glad to work with Kernkonzept to drive the safety and real-time operating system world.
Yeah. All right. So let's get started with the presentation. So today we are talking about safe and secure heterogeneous compute with the L4Re Hypervisor family. So what does this actually mean? So when we talk about heterogeneous compute, specifically in the ARM context, we're talking about systems that consist of Cortex-A and Cortex-R, processors that somehow are sitting close to each other and need to be handled from a software perspective. And we want to show how the L4Re hypervisor family can help to master the complexity that comes with such kind of systems. So digging into it, so what are we seeing? So everyone is talking about the software-defined vehicle and automotive, and what does it actually mean from our perspective of the consolidation part that is coming with that. So software is more and more defining what a car is providing as a value to the customer. So people going for cars because of features that are coming along that are purely based on software, so be it navigation or assistance system whatsoever. Nobody is is going for a particular car because it has a certain brand of brakes, for example. So software is defining what a car is, and because software is such a crucial part, is getting more and more important. More software needs to be put on the car, but unfortunately, the current way of building cars or the current IT architecture of cars cannot cope with the increasing software features we want to put on a vehicle. So adding more ECUs, adding more cabling is just not possible because the 100 ECUs that are already there cannot increase because there's no space, no weight, no energy, and so on for those kind of systems. And the same goes for the cabling. The kilometers of cabling which are in there cannot just be increased because it's already on the limit. And additionally, with that, so the hardware is also getting more powerful, which also calls for the consolidation case that we can bring more software onto less hardware, basically. And that actually requires from the hardware that the hardware needs to cover a wide range of different kind of functionalities, which we'll be looking into shortly. So while we are talking about automotive use case, the automotive market today, similar considerations are also possible for other markets where similar requirements exist. All right, so let's look a little bit into what kind of hardware challenges are there for when building hardware for specific for specific requirements. So, for example, when we look at safety, the safety requirement from a hardware perspective, there are processors being built specifically for safety, which have additional functionality to make to fulfill the safety requirements, and there are processors which not suitable for safety. They don't have those means. They're less costly. Similar consideration goes for real time, for predictability and throughput. So CPUs having lots of throughput, they are not as much predictable as required for real time use case. And similar considerations are taken for power consumption versus performance, and also for generic compute and versus some acceleration or some specific piece of hardware that does one thing very well, but just this one thing compared to general purpose CPU that then obviously doesn't do this particular thing as performant as a specific function. And because we have all those requirements in a vehicle, basically, that means that we need to have all those kind of function blocks in an SoC in a car, which we somehow need to cope with as a matter of fact. So now when we look at this from with ARM systems in mind, so we basically see two different kind of focus points in the processor design. So on the left side, we have the Arm Cortex-R profile processors that are targeted at small-scale systems and very much focus on the safety and real-time requirements of the use cases. On the right side, we see the big-scale systems typically handled by the Cortex-A profile processors that are very much performance oriented. Also from another difference basically is also the number or the amount of resources available for those kind of systems. So the Cortex-R systems are typically resource constrained, and the Cortex-A systems, at least in the bigger system, they typically have plenty of resources or can be equipped with plenty of resources. One difference between the Cortex-R and the Cortex-A profile processors is really from an architectural perspective, that the memory protection that both systems offer is different. So the Cortex-R systems have a memory protection unit that allows to separate memory in a region-based way, and the Cortex-A processors on the other side, they have virtual memory, allowing really much more flexibility with respect to memory handling and separation. All right, and the other thing we see is that both profiles move closer to each other. So the Cortex-A systems get features that have been previously only available for the Cortex-R. So, for example, the safety features are being added to Cortex-A processors, and on the same side, or on the Cortex-R side, also features are added to that have been only available on Cortex-A previously. So, for example, virtualization features, which is now available. So to summarize that, both the Cortex-A and Cortex-R profile processors, they target different kind of use cases, but are moving onto each other basically, with only the little difference in the memory protection that can be handled by software abstraction layer, but otherwise they are based on the same architecture, and which we can leverage in our work. And just to give you one example on each of the profiles. So on the Cortex-A side, for example, there's the AE versions of the Cortex-A processors, with one example being the Cortex-A 76, which got safety features and can be used in a safety environment. And on the Cortex-R side, the Cortex-R52 is the first processor that implements hardware-based virtualization, which is really nice for supporting this kind of consolidation use case we are talking about here today. Okay, so now when we look at a heterogeneous hardware platform, or a hardware platform that is typically used, so this is it's an example, it's a made-up example, but what we generally see is that an SoC consists of multiple different kind of compute units. So there's a Cortex-A cluster, for example, where you run your Linux or other rich OSs. There is a Cortex-R cluster where you run your autos workloads on maybe. Then there can be a GPU for doing GPU related things. There can be an NPU for doing AI related things, and obviously there are also the standard blocks you would need, like memory, communication network, PCIe, and so on. Now, when we look at this from a software from a software perspective, so what is being done there? So each of those processors on those SoC typically run their own software stack, or they run their own RTOS with their own software stack. And so one can be, for example, a classic AutoSAR, and another RTOS is a different variant of that. And the multi-core or the Cortex-A processor runs definitely a different kind of software stack. So there might be a hypervisor in there, might not be a hypervisor in there, or just a rich OS, but it's definitely something very different from what is running on the Cortex-R side. And the point really being is that the software that is being developed for such kind of systems is very tailored and very much adapted to the particular hardware. And now when you want to change anything in this stack, you have a hard time doing this easily without putting much engineering effort to change either this architecture or exchange some parts in the architecture, like exchanging a piece of hardware or doing this on a new on a new hardware. And actually what we actually want is to have this kind of flexibility, that we can easily or relatively easily get the flexibility in the architecture to be able to change those kind of, or to change the software components and decouple them from their tight coupling to the particular hardware. So now moving over to the what the software defined vehicle. So that's the target basically that comes out of the wish that a car is defined by software functionality that what comes out of this requirement that the car is defined by software is that we really need an independence of the software, or the software functions that actually implement something, that this is not really dependent on the hardware, and that when you change the hardware or slightly change the software, that you have a big engineering effort of actually doing this. So if the software is independent of the hardware through a proper layer of software in between, that very much helps you to gain this flexibility and scalability that we all need to implement an SDV concept. The other points also being that this kind of flexibility actually helps you to design a system according to your performance and price and availability constraints that you might have as someone building an ECU. And the other points being, or which are important here, is that the independence of the software components to the hardware, as well as the software components among each other, is that obviously you can have much easier time implementing a software lifecycle or a software lifecycle for individual components, which is obviously very useful, or very useful to update this kind of components and also doing all the certification needs that the software in a vehicle in a car needs. So for certification, it needs to be both safety certification and other parts or same parts of software also need security certification. And if the dependencies of the software components are as few as possible, that makes all those processes be easier to accomplish. Yeah, and not to forget what I already mentioned is a decoupling of software components from the hardware also allows you to update those software components independently and also update the hardware, which might be required either because the lifetime of the software or the lifetime of the car, and so it's the lifetime of the software running the car, are much or can be much longer with the 10 to 15 years as hardware might be available, which might make it necessary to update the hardware as well. All right, so when we now look at the picture we have seen previously, we can now add such a abstraction layer, which I've put in here. So on the top, we still see the same kind of software components running there or software ecosystems running there, but there's an abstraction layer now. And this abstraction layer gives us the opportunity or gives us the features that with a uniform API, which this abstraction layer provides, it allows us to flexibly put those software components on the top on either of the processors which we are seeing there. So might be you have a Cortex-R processor or Cortex-A processor or any combination of multiple numbers of those. You can put it there as there is availability or requirements on the hardware and on the software. And that's actually what we are providing with our L4Re hypervisor family, and that's where we'll have a look into right now. So everything is actually based on the L4Re Operating System Framework, and the framework is an operating as a modular operating system that has all the building blocks to build system tailor-made for your use case, and only basically contains that what is required for that use case, building a minimal setup of functionality exactly for the use case you are looking at. To make this a little bit more practical, I have brought this little example. This is actually a demonstration we have built, and I very much invite you to watch a demonstration of the demo on YouTube after this talk. And yeah, what are you seeing here? So on the right side, you see a setup of the L4Re hypervisor that is running on an Arm Neoverse cluster. So in this very much demo, it's an Atlas Ava platform. So it's running 2 VMs. It's also running a supervisor component, and by the VMs, or they're just Linux VMs, nicely isolated by the L4Re hypervisor. The supervisor component is actually interesting here because it provides, or it's a component that's running directly on the hypervisor and exploiting the features of the L4Re Operating System Framework to build it as small as possible without any third-party dependencies like on the VMs or similar, giving you exactly the smallest possible code base for such a functionality. And you might imagine the supervisor is can be or is a super critical component in the system, ensuring that all the other components work correctly. So it's very crucial to make this as small and as understandable as possible from the amount of complexity or non-complexity that goes into it. So this system is running on Neoverse, so classic server or Cortex-A based system. And when we now go to the other part of the demo, we are running similar setup on Cortex-R52 platforms. On the demo, it's an NXP S32Z. That is also running a couple of VMs. So in this case, it's Sapphire VMs and FreeRTOS. It also has a supervisor, which is the very same supervisor running on the R52. Also as a native L4Re application. And and just to give you some ideas on the demo actually. So what the demo is actually also showing as an automotive use case is that the one VM on the L4Re hypervisor is running a large part of the OpenAD software stack, and one thing has been taken out and moved over to the R52 system, showcasing basically the safety island case in that demonstration, that this autoware actuation component is running on the R52, doing actuation work, and all the heavy computing with route planning and so on is all done on the powerful Neoverse system. And in this demo, they are all connected via Ethernet. And please check out the YouTube video for further info and actually seeing the demonstration. All right, so what does the L4Re operating system give to you? So we have the L4Re hypervisor family, which provides you this uniform API for your applications, and that actually gives you the flexibility and scalable system architecture that is required to build the software-defined vehicle. L4Re also uses an object capability-based design, being the state-of-the-art on how operating system and hypervisor-based security should look like. So it's very well covers the security aspects of such a system, and also through the modular design. It allows you the small trusted computing base, which are actually application specific, because every application on the L4Re system has their own TCP, obviously, and this also contributes to the security properties of the system. The modular structure also gives you other benefits, such as the path to security and safety certifications is very, very strong and manageable because of the modular structure. Only small components need to be looked at, and all the components not related to any of security and safety can be nicely encapsulated in, for example, VMs or other L4Re applications, and you don't need to look at those for those particular reasons. Not to forget, L4Re is an open source system, so it's it's available to you to look into it, and this also helps transparency and trustworthiness of the system, obviously. And yeah, obviously it runs in Cortex-A and Cortex-R. Yeah, so a few words on what Kernkonzept is doing here. So we are developing the L4Re Operating System Framework, which is a system composed of building blocks, as you see in the graphics, and we actually help customers to build their products tailor-made for their use case, such that their requirements are met as best as possible. Yeah, and I also want to have a look at SOAFEE, and so SOAFEE is a industry-led consortium that looks how to define or how to shape the software-defined vehicle from a systems perspective, and obviously a hypervisor technology is very much of the core of that, being able to consolidate multiple workloads on a single ECU, on a single system, and it also doesn't stop at the core itself. It also moves on to the cloud, where you can implement use cases like having a digital twin, or having software development there, software in the loop, and all those properties one gets when having a similar operating environment, similar operating environment also in the cloud and in the car, giving you the option that the components you have in the vehicle you can also deploy in the cloud, be it for development or be it during also operation of the car. So this concludes my my part of the presentation, and now Jan will show you the demonstration and guide you through the rest of the presentation.
Yeah, thanks, Adam. I hope you got a glimpse on the challenges that the automotive industry is facing here. And so what we show you here now in the next minute is the L4Re system as it runs in the Arm FVP simulator. And when Adam gave the introduction to the demo that we have shown that is available on YouTube, this was actually two systems. The Cortex A profile system with the Neoverse and the Cortex-R. They are connected to each other, but they are still separated from each other. And but the Cortex-R R82 is now taking this to the next level, because it is more or less a unification of both these different kinds of systems on the same processor. With the Cortex-R 82, ARM has created an architecture and an implementation where you can have a real-time hypervisor with real-time guests, but also can run standard Cortex-A line operating systems as Linux. And this is what I will show you in a minute. And what you will see is the L4Re micro hypervisor running on a simulated 4-core Cortex-R 82, where two of the cores are available to the Linux VM. It's a standard Linux kernel just taken from kernel.org, so there's no modification needed. And on the other side, there's a Zephyr VM, which is also vanilla and has not been modified in any way, which is running as a demo for real-time guest. And actually, both VMs are sharing one of the CPUs. And to make this more approachable and to have an interaction with that, we have also the console multiplexing application, which is also again, a native L4Re application. And this one enables us to see both output of both VMs and also interact with them individually. Yeah, so to show you that, I will have to hand over to my laptop here. Let's see if that works. So here we go. Okay, so actually, in the previous slide, there was one icon on the bottom right where you saw the GitHub icon. And when you have the slides available afterwards, you can click on that icon because this demo that I'm showing here is available on GitHub for everybody. So can you build it? You can build it yourself. You can tinker with it as you want and try it out. So if I start it now, what you see is first the L4Re system booting quite quickly. And then the output of the different components that we have here. I forgot to mention there's a I/O component, which is a L4Re component to separate the hardware for the different guests. In this case here, we only have a simple PL011 UART, which is forwarded to the Linux guest, but it could be much more complex. And as you can see here now, Linux is booting in the background. The Zephyr VM has already started because it's such a tiny operating system, and Linux just needs more time to come up. And yeah, actually now you can see that it has booted. Let me stop that here briefly for a moment. So this is now the input for the console multiplexer. And we can see all the clients that we have. We have the Linux, we have the Zephyr, and we have this I/O component that separates the hardware for the different guests. And I can now connect to the Linux VM. And yeah, have a more or less simple BusyBox shell. So it's not a quite sophisticated system. We have, we have two processors here. It's running in an SMP configuration. And we can also connect to the Zephyr VM, which is just printing a Hello World application. But it could be so much more. What also comes with the L4Re operating system, because it's microkernel based, we also have a built-in kernel debugger. This is quite a sophisticated tool. So I will just show you briefly what it could do. For example, you can see all the threads that are running here. You can peek into the system state of one of the CPUs if you want, if something happens with your guest, if it's not working, if it's not responding, and so on. You can also view all the different objects that are handled by the kernel to deeply analyze the system as something goes wrong. So this is very valuable to debug such complex systems if you need to. Okay, so I will hand over to the demo, to the presentation again. Okay, here we go. So yeah, so to wrap things up a bit, the L4Re Hypervisor family now provides you this uniform abstraction that you can run your different operating systems, be it Linux, be it some Zephyr, be it some FreeRTOS or whatever, to run it inside a VM if you need, and you can deploy it on Cortex-R, on Cortex-A, and it's a uniform API that everybody can use there. So for the Cortex-R parts, we are running on the NXP S32Z. Actually, NXP is providing the green VIP reference stack for their SoC there, and L4Re is the reference hypervisor that is included. But of course, we are also running on the ST Stellar, the Cortex, the Renesas R car platform, and as you just saw on the Arm FVP. On the Cortex-A side, there are vast majority of systems that we can run on. L4Re is, as we think, system ready. It's not certified, but on the AVA platform, it's putting in a system ready mode. So we are quite confident that it's for any system ready system that we can put there. Of course, it's running on the S32G from NXP, Raspberry Pi, you name it. So just ask or look at the GitHub code. And as I said, it provides the uniform API. You can build native application on L4Re. So it's not just a hypervisor, but it's a full-fledged operating system. You can write in C, C++, and also Rust nowadays. And for the hardware virtualization, L4Re is using all the stuff that the hardware gives us to run the VMs as fast as possible and to isolate them. And yeah, we are providing standard VirtIO APIs for everything that's needed and also emulate devices as required. And for the future, we are also in the SOAFEE context try to enable lightweight containers for the small scale systems so that you can deploy on the Cortex-R where you normally have tightly coupled real-time operating systems with the hardware, that we enable there something containerized to easily deploy workloads on the Cortex-A side, as you are now used to have on the Cortex-A side even today. Yeah, to summarize, L4Re provides this uniform abstraction layer to build software-defined vehicles in the future, to have the hardware and the software decoupled from each other, so that you can update them independent, more or less, of each other. Yeah, so it's a very wide range of computing that we can enable with the same APIs. And I think we provide the scalability and the flexibility that OEMs will need in the future to build their ECU architectures and deploy their software as required. Yeah, that basically brings me to the end of the talk from us, and we are happy to take questions.
Thank you, Adam. Thank you, Jan. Yes, let's get you both in shot. There you go. Thank you for an awesome presentation and a great demo. And for those on the Zoom call, I have on the Zoom webinar, I pasted a link to the GitHub in the chat, to the GitHub link in the chat. So please check it out there. I've got a couple of questions for you guys, and I know questions are coming from the audience, so please do get them in. This is your opportunity to ask the folks from Kernkonzept your burning questions about this great technology and about its applications in the automotive space and beyond. I want to start talking a bit about SOAFEE, which you mentioned earlier on in the talk, and obviously that you guys work very closely on, and we are, and Arm also is one of the founding members of. From the L4E aspect, does that actually run in the cloud?
Yeah. Oh, very good question. Yeah, actually it does. So Jan already mentioned that L4Re is system ready, and as the cloud solutions we have today, like AWS on Graviton, is also system ready. It's just with there's no change required basically to run it in the on Graviton in AWS, and we are actually working on providing some good examples in that environment to make it easily accessible for everyone.
Awesome, thank you. And you touched on Cortex-R, right, quite a bit in your presentation, and what I'd love to get is your thoughts on the role of, and how important the role of virtualization is going to be in this space, in the Cortex-R space. What would you like to kind of add to that point?
Yeah, I think on the Cortex-A side, virtualization is quite common nowadays, and I think it's getting more traction on the Cortex-R side, the Cortex-R52 being the first one where you can have it in silicon available. And I think it's very much required by the consolidation use cases that the automotive industry is facing. And I think there's quite a lot of need to have virtualization on the Cortex-R available to consolidate the different ECUs into common systems. I still think there's quite a lot of way that the industry has to go, because on this real-time systems, this is quite new, but I think the requirements will drive the industry there. And it's a tough road, but I think it's coming in the next years.
Brilliant, thank you. That's really, really great. I'd love to kind of get your thoughts on that sort of topic. And I'd love to jump to the audience questions now. So audience, if you've got any particular question that if you're looking at the Q&A box and you see one, you think, oh, I'd like that one to get bumped up to the top, just hit the little thumbs up icon and I'll make sure that one gets asked next on the list. And do get your questions in. We've got a good 5+ minutes or so, maybe up to 10 minutes if we push it to get your questions in. So let's go for it. Is there any standard benchmark used to compare hypervisor solutions?
Oh, well, I don't think there is a standard benchmark for that, because also very much depends on which which area you want to look at. So I think in the embedded embedded area where resources are where systems are resource constrained, people very much look just into compute, how compute behaves, virtualized versus non-virtualized. So there's you could use Cormark, for example, as a very basic kind of benchmark. There are others like VBench, for example, to mention, which is more application-based use cases, but still, in the end, different kind of compute things. Yeah, and then I think all the other benchmarks which are typically used on the server side is hard to use in the embedded area. So I think that's very much focused on that kind of benchmarks, on compute kind of comparisons.
And I think from the Cortex-R side, I think there's quite a lot of they are missing, because people there are typically concerned about latencies, and I think there need to be some good benchmarks. I mean, we do the micro benchmarks for our stuff, but there's no established industry benchmark yet. I think that's missing.
Brilliant. Thank you both for that. Great detailed answer. And we've had another question coming about how L4Re compares to Xen or XEM on there. Do you want to take that?
Sure. Yeah, sure. So I think there's one fundamental, or some fundamental differences. So Xen is based on an architecture where you have a DOM0, it's called. So it's a virtual machine, typically Linux, that has all the hardware and basically drives the system. So from a security perspective, the DOM0 is part of the system and needs to be trusted. In L4Re, in comparison, being a microkernel-based system, you could build something like Xen, but we would not recommend this, obviously, because in L4Re there's no such central VM, which is absolutely required to build a system. And also Xen is a hypervisor, so it can run VMs. Obviously, that's the job of a hypervisor. But it, if you want to have something outside of VMs, like we have with our native micro apps, there's nothing comparable on the Xen system. And we know that there's work by several people work underway on Xen to work on those parts I just described. But overall, the main difference in the architecture is just as I described. All right.
Thank you both for that. And actually, so on the similar vein, there's a question that's come in on kind of how the solution differs to other hypervisors. Is this only for ARM v8R cores, and where does the actual coordinator software run? Don't know if you want to take that one next and add anything over to that response and take it further with this one.
So could you repeat? I didn't get the question correctly.
Sure. How is the solution different to other hypervisors? Is this only for ARM v8R cores, so Cortex-R cores? And where does the actual coordinator software run?
Okay, good. Okay, thanks. So L4Re is not only for ARM, so we also run on other architectures, which also exploit the virtualization capabilities there. And from an architectural perspective, you might have noticed that in some of the pictures there was a component in there which is called VMM, which is a virtual machine monitor actually. And from an architectural perspective of L4Re, there is a separation between the functionality you need in the hypervisor, so running in the privileged mode of the CPU, doing the switching of the VMs and taking care of the memory separation or providing the proper memory to the VMs. And on the other side, having actually the virtual platform defined and implemented with virtual devices and bringing life to VM. That is implemented in the virtual machine monitor, and in L4Re context, this is just in quotes, this is just an L4Re application running next to another L4Re application and being a VM. What we typically do is we have one VMM per virtual machine monitor, exploiting the isolation properties of the hypervisor into that architecture, meaning if potentially a guest could break out from a security perspective, could break out of the VM, it still would be contained within this box implementing the virtual machine to the virtual machine monitor. So this gives basically multiple layers you have to overcome as from a security perspective to interfere with other components in the system. So this also makes it very attractive from our perspective for security related use cases.
For sure. And we've had still a couple more minutes left. I think we can grab in slot in a couple more questions. One is, what is the ASIL level certification for the hypervisor?
Oh, that's actually a good question. So regarding safety certification, we are working together with Electrobit, and the hypervisor is supposed to be available in ASIL B this year. So we've been working on this for some time, and we are very happy and also proud that the L4Re system we are working on, which is open source, is now soon ASIL B certified for automotive. I think this is very cool.
And of course, I mean, that would not be the end of the road. I mean,
obviously, yeah.
On our roadmap, it's of course ASIL D. I mean, that's the one, that's the benchmark that we need to get.
Yeah, absolutely. Yeah.
No, absolutely, that's really exciting. So no, that'll be great once that comes through for you guys, for sure. And let's get one more final question in, which is a top voted one right now. Is there a potential for real-time analytics to be used on embedded solutions, or for embedded solutions, say healthcare, real-time traffic, or something that is time-bound?
Yeah, absolutely. So actually, the L4Re initially started. So L4Re has a long history. We didn't go into detail on that. And one of the first focus areas was actually real time for the system, and it's still in there. So absolutely, our real time use cases are very much possible with the system. And yeah, anything to add? No.
Awesome. No, thank you both so much. And I think we're going to just about wrap it up there. Before we do, Adam and Jan, thank you again for an awesome presentation, some great content, and thank you, audience, for your great questions. And we're very much looking forward to seeing you in the next week's presentation from Sonatus and the week after from NXP. But before I finish wrapping up, Adam, Jan, is there anything else you want to add as a final note for our audience? Final call to action?
Yeah, no, thanks to everyone for listening today. And we're happy on any feedback and comments. And thanks to you, Tobias and Arm, for having us in this tech talk. It was very much fun. So very much enjoyed it.
Our pleasure.
Thanks to all of you. Yeah.
Our pleasure. Absolute pleasure to host you. Really, really great content and demo. Thanks again, audience, for your great questions. There's so many coming. I know we didn't have time to get to all of them, but do reach out to the folks at Kernkonzept and they'll have hopefully all the answers, or as many answers they can give. I'm maybe over-promising there, but I'm sure they'll have as many answers they can give for your questions. So thank you so much for those fantastic questions. Great content, great demo. And we look forward to seeing you next week for another Arm Tech Talk with an automotive theme from Sonatus. And again, if you like what you see, make sure you subscribe to our YouTube channel. Sign up for upcoming tech talks for all the latest trends, technologies, and best practices from Arm and our ecosystem partners. Thanks so much for joining. We'll see you again next week.